This is the notebook that builds the transformer from a single attention operation all the way up to a full model that trains on next token prediction, and then loads real GPT-2 to inspect what it learned. Here is why it matters. Implement multi-head attention from scratch is the single most common coding question at Frontier Labs, and if you cannot do it, you will not pass the technical screen. We are going to build every piece by hand, understand why each one exists, and finish with you able to write the whole thing on a whiteboard in a few minutes. Forget neural networks for a second. Imagine a normal dictionary. You hand it a key and it does exact matching to return one value. Attention does soft matching instead. You hand it a query. It measures how similar that query is to every key, turns those similarities into weights that sum to 1, and returns a weighted blend of all the values. So instead of one exact hit, you get a smooth mixture, weighted toward the keys your query resembles most. Hold that picture, because the entire mechanism is just that idea written in linear algebra. The notebook makes that concrete in about 10 lines before defining any class. You start with 3 matrices, queries, keys, and values, 1 row per token. You multiply queries by the transpose of keys to get a similarity score between every query and every key, and you divide by the square root of the key dimension, which we will justify in a moment. You run a softmax across each row so the weights for each query sum to 1, then multiply those weights by the values. The output has the same shape as the values, 1 blended vector per token. When they plot the weights as a heat map, the rows are query positions and the columns are key positions, and every row is a probability distribution over all the keys. That is the key observation. Each token produces its own distribution over what to look at, and its output is the weighted average of every value. This is exactly how attention lets every token look at every other token at the same time, in parallel, with no sequential bottleneck. That parallelism is the whole reason transformers beat recurrent networks. Let us name the limitation attention solves. A recurrent network reads a sequence one step at a time, squeezing everything it has seen into a single hidden state, so information from a distant token has to survive a long chain of updates to reach the present, and gradients fade along the way. Attention throws that out. The path length between any 2 tokens is 1, they connect directly, and the whole sequence is processed at once rather than in order. That means better gradient flow over long distances, and full use of the parallel hardware we train on. Now we make it learnable. So far queries, keys, and values were just given, but in a real model they come from the input itself. You take your input, 1 vector per token, and pass it through 3 separate learned linear projections to produce the queries, the keys, and the values. So the same token gets cast into 3 different roles. What am I looking for? What do I offer as a match? And what content do I carry? Those 3 projection matrices are the parameters the model trains, and they are where attention actually learns relationships. Here is the question every interviewer asks: why scale by the square root of the key dimension? Think about the dot product of 2 random vectors. Each is a sum over the key dimension of products, and as that dimension grows, the variance of the dot product grows with it, roughly proportional to the dimension. Large scores push the softmax into its saturated corners, where one weight is almost 1 and the rest are almost 0, and in those regions the gradient is nearly flat. Dividing by the square root of the key dimension pulls the variance back to about 1, keeping the softmax in a healthy, trainable range. The single-head attention class is small and worth memorizing. It holds 3 bias-free linear layers for the query, key, and value projections. In the forward pass, it projects the input into all 3, computes the scaled dot product scores, applies the softmax to get weights, and multiplies by the values. It returns both the output and the weights, because those weights are what we will visualize later. That is the entire scaled dot product attention, 4 operations wrapped around 3 matrices, and the shapes flow cleanly from input to output. For a model that generates text left to right, a token must never peek at tokens that come after it, otherwise it would cheat by seeing the answer. We enforce that with a causal mask. Before the softmax, every score that points to a future position is set to negative infinity. When the softmax exponentiates negative infinity, it gets exactly 0, so those future positions receive 0 attention weight. The notebook builds the mask as the upper triangle of the score matrix, and then verifies that the masked region really is all zeros after the softmax. That is autoregressive attention in one move. A single attention head can only learn one kind of relationship at a time, but language has many overlapping structures. One token might care about the word right before it, another about the noun a pronoun refers to, another about syntax. Multi-head attention runs several attention operations in parallel, each with its own projections, so the model can attend to different relationship types simultaneously. Then it concatenates what every head produced and passes it through one more output projection to mix the results back together. More heads, more kinds of relationships captured in a single layer. Now the part candidates get wrong on the whiteboard. You do not actually run several separate attention modules. Instead, you project to the full model dimension once, then reshape that into many heads by splitting the last dimension and moving the head axis up front. So the tensor becomes batch by heads by sequence by per head dimension. Attention then runs batched across all heads at once, which is far more efficient on a GPU. Afterward, you merge the heads back by reversing the reshape and apply the output projection. Getting that split and transpose right and remembering the scaling is the whole exercise. One detail that makes stacking possible. Multi-head attention takes an input of shape batch by sequence by model dimension and returns output of the exact same shape. The dimension per head is just the model dimension divided by the number of heads, so concatenating all the heads lands you right back at the full model dimension. Because the output matches the input, you can stack these blocks as deep as you like, each one refining the representation. The notebook checks every shape with assertions, which is a good habit to copy in an interview. The notebook visualizes the weights from all 8 heads side by side. At random initialization, they look like noise, every head roughly uniform, because nothing has been learned yet. The point is to see that each head has its own independent pattern that training will sculpt into something meaningful. Later, when we look at real GPT-2, you will see these same plots filled with sharp structure, diagonals and columns and pronoun links. Same visualization, untrained versus trained, which makes the learning visible. Here is a subtle problem. Attention is permutation equivariant, which means if you shuffle the input tokens, the outputs just shuffle the same way. The computation itself has no idea what order things came in. But order is meaning in language. Dog bites man and man bites dog use the same words and mean opposite things. Recurrent networks get order for free because they read in sequence, but attention sees an unordered set. So we have to inject position information explicitly, and that is what positional encoding does. The original transformer adds a fixed positional encoding built from sines and cosines. Each position gets a vector where different dimensions oscillate at different frequencies, computed from sine and cosine of the position divided by a geometric range of wavelengths. That gives every position a unique fingerprint, and crucially the relative offset between two positions can be expressed as a fixed linear transform of their encodings, which helps the model reason about how far apart tokens are. These encodings have no learnable parameters, so the notebook stores the table once as a buffer and just adds it to the embeddings. When they plot the encoding, the structure is beautiful. The high-frequency dimensions flip quickly from position to position, so they pin down fine-grained exact location. The low-frequency dimensions change slowly across the whole sequence, so they capture course, where am I roughly positioned. Together they form a multi-scale code, very much in the spirit of Fourier features, where combining many frequencies lets you represent both the broad strokes and the fine detail of position at the same time. Attention mixes information across tokens, but each transformer block also needs to think hard about each token on its own. That is the feed-forward network, a small two-layer perceptron applied independently to every position, expanding to a wider hidden dimension, passing through a smooth jello activation, then projecting back down. One useful mental model from interpretability work is that these feed-forward layers act like a memory that stores factual knowledge, while attention does the routing. The notebook uses jello rather than ReLU because its gradients are smooth right around zero, which trains a little more gracefully. Now we assemble a full block, and two ingredients hold it together: residual connections and layer normalization. The residual is just adding the sublayer output back onto its input, which gives gradients a clean highway straight through the network and lets each layer learn a small refinement rather than a full rewrite. Layer norm rescales activations to keep them well behaved.